In this video we show how to trace the pH curve of a titration of hydrochloric acid with sodium hydroxide. Right, so this is an example of a titration curve for a strong acid being titrated with a strong base. And the goal is to calculate how the pH changes as you start with only acid and then start to add increasing amounts of base. Right, so we have to build a table in which we simply calculate the pH, that is our goal, as a function of the volume of sodium hydroxide added. Okay, so we're going to add no volume, so that will be the start of the titration. So in this case you only have the acid, then we will add 10 mils of sodium hydroxide, then 20, and then 30. Okay, and the parameters are that the molar concentration of sodium hydroxide is 0.1 molar, and we're titrating 20 mils of hydrochloric acid, which is also 0.1 molar. Alright, so let's try to do each one of these calculations in turn. In order to do the calculation successfully, the first thing that we have to consider is what is the reaction that is behind the titration. And the reaction is simply an acid-base reaction where you have hydrochloric acid reacting with sodium hydroxide to generate salt and water. Alright, so this reaction is going to allow us to carry out stoichiometric calculations to be able to determine whether we have acid or base in excess and how many moles and the concentration of that acid or base we have, which in turn dictates what the pH is. Alright, so let's go step by step. First point, we have only the acid, no base has been added. This is a trivial calculation because this is strong acid, and then we know how to calculate the pH directly. For that first point, what we'll have is that the pH is simply the minus base logarithm of the concentration of protons, but we have that as an initial piece of data, right? So this is simply going to be pH 1.0, right? The pH of a concentration 0.1 molar of a strong acid happens to be 1. In this case we have 3 significant figures, so that is our pH, 1.000. Right, that is the simplest point, or one of the simplest points in the entire curve. Let's go to the next one, which is more interesting. What happens when we add 10 mils of sodium hydroxide, 0.1 molar? Right, so here we already have to think about the stoichiometry of the reaction. So we have to think about this in terms of moles of acid reacting with moles of base. Right, notice that the moles of acid, when you put this together, is going to be equal to 2.0010 to the minus 3 moles. Right, so we can build here a table where we can write the moles before reaction and after reaction. Alright, so before the reaction we will have 2.0010 to the minus 3 mole, and then the amount of moles of sodium hydroxide that we're adding would be those given by 10 mils of 0.1 molar concentration, and that amounts to 110 to the minus 3 mole. Okay, so initially of base we have 110 to the minus 3 mole, and then we won't have any initial products, but that is relevant to our calculations. Alright, so clearly because the stoichiometric coefficients are 1 to 1, then acid will be in excess at the end of this addition of base, and all of the base will be consumed, right? So this gets to 0 after the reaction, and then the amount left over will be 1.0010 to the minus 3 moles of the acid. Right, so from these moles then now we can calculate what the molar concentration is of the acid, and therefore the pH. Okay, so the important thing here is to actually be very careful about the volume in which those moles are. Notice that we started with 20 mils of the acid, but because we have added now 10 mils of the base, the total volume is 30 mils, and that matters to calculate what the concentration is. Right, so the concentration of protons at that particular point will be the number of moles that you have, 1.0010 to the minus 3 mole, over the total volume, which is 10 plus 20, that will be 0.030 liters. Okay? So that concentration then happens to be 0.030 0.333 molar, okay, which then you can take the minus based on logarithm of, and then that gives you the pH. And the pH corresponding to this molar concentration of protons happens to be 1.477. Right, so this is our second point in the titration curve, and you can clearly see that the expectation is borne out. We're adding base, so again we expect that the pH should increase from the initial pH 1 to again ever increasing pH as you add more base. All right, let's go to the next point in the titration, which is going to be fairly simple. All right, let's think about what happens when you have 20 mils, when you add 20 mils of the base. Right, so you can quickly recognize that at this point you have the same amounts of acid and base. That is what we actually call the equivalence point, and that means that there's none of them is in excess, right? So you will have that in this, but for this particular case, 20 mils, that is the stoichiometric or equivalent point in this particular case, and that means that there's no excess of reagents or products, right? They will be both 0 after the reaction, and then you have a neutral solution. The pH will be 7. Okay, so for this particular case, the pH is going to be 7. All right, and again, notice how the pH continues to increase here. All right, let's go to the last point that we have here, 30 mils of the base. You can clearly anticipate that because we're past the equivalent point, any more base that we add past that point will result in a basic pH. Right, so that is the expectation, and what we have to do is see if that is borne out by the calculations. Right, so we come to our table here, and then the amount of moles that you have, if you have 30 mils of 0.1 molar base, then there will be a number of moles of 310 to the minus 3. Clearly, you can see that now the limiting reagent is hydrochloric acid, and you will have excess base, so that is going to result in a basic pH for sure. Okay, at the end of the reaction, then you will have 1.0010 to the minus 3 moles of the base left over. Okay, and then from there we have to calculate the pH. Now notice that a common mistake here would be to simply assume that this is the concentration of protons that you have, but that would be erroneous. Notice that the reagent that is in excess is sodium hydroxide. So actually this concentration or these moles is not of the acid, but of the base, right? So make sure that you consider that. Your calculation of the base, or its minus now, will be 110 to the minus 3, and very important here, the volume will be 50 mils as opposed to just 30. Notice that the volume will be the 20 that you have initially, and then the 30 that you have added. That corresponds to a volume of 510 to the minus 2 liters. Okay? With that, your concentration of OH, hydroxide, is 210 to the minus 2, and from here we can calculate what the POH is, right? If we take the minus based on logarithm of that number, we'll get to the POH, which is 1.699, and from here you can calculate that the pH will be 14 minus that number, which is 12.301. Alright, so we have our last point here in the table, 12.301. Okay, clearly showing that we're past the equivalence point and the pH has turned basic. Now for good measure, we could actually add one more point, which is illuminating in this pH titration curve. Right? We could actually see what would be the limit. Suppose that we add an infinite amount of the base. What would be the pH then? Well, if you add an infinite amount of base, then you will, to a great approximation, to a good approximation, have only base, right? So the pH will be dictated by the pH of the base. Because the molar concentration of the base is 0.1 molar, then the POH will be 1, and then the pH will be 13, right? So the highest ever pH that you could get in this titration would be 13. Okay, and in between those points, the initial and the end, then you trace the pH curve that would look like this. Right, so if we were to actually draw how that pH curve looks like, it will be something like this, right? So here you will have 10, that will be 20, that will be 30, and then infinity, that it will be the volume of sodium hydroxide in mils, and this is the pH. And we can put here 1, and we can put there 7. Here we can put 13, right? So if this is 13, then at infinite volume you will reach that limit. Okay, and then at volume 7 we have, volume 20 we have pH 7, and then at volume 0 we have pH 1, volume 10 we have 1.477, and then at volume 30 we'll have 12.30, so we'll be right around here. You can clearly see how this is an S-shaped curve. Okay, that is how the titration curve for a strong acid with a strong base looks like. All right, so in this video we have carried out quantitative calculations for how the pH of an acid-base titration changes as you add base to a strong acid.